Again, welcome to DSRT 734 class, Inferential Statistics in Decision Making. These lectures cover the fitting a linear model. So our main objective is to learn how to create a linear model using a data set. So we start with the linear equation, and the definition here is the same concept as a college algebra linear equation. Here we said that if two variables appear to be related in a straight line manner, we can use the linear equation to model their relationship. And this will lead us to the concept of regression analysis or using regression modeling system. So let's start with the linear relationship definition. Here we say a linear relationship is graphically described as a line, or mathematically a line is a set of points that satisfy the functional relationship y equal to ms plus b. Again, we learned this in college algebra where m is the slope, x will be our independent variable, b will be our y-intercept. Y-intercept means when s equal to 0, the value of y. So here we say m is the slope of the line, b is the point where the function crosses the y-axis. Also, it's called the y-intercept. Now, what is a slope? A slope normally would determine if the line slopes upward, that's a positive slope, or if the line slopes downward, negative slope. And also the steepness of the line. So when the slope value is very big, the steepness is very high also. So this example of a linear relationship, here our first diagram shows that when s increases, y also increases. We can see from the pattern of the points. Now on the green graph, we can see that when s increases, y decreases. We can see the line is going down as s increases, the pattern. Now with the gray, which is our third graph, the gray, here we can see that there's no relationship. As s increases, y does not change in predictable way. Now we can see that all the points are just scattered all over the place. So this is the concept we cover in our previous lectures when we studied the relationship correlation analysis or finding the correlation coefficient. And the first diagram with the orange background will give us a positive R value. The green diagram will give us negative R value, that's the correlation coefficient. And the gray will give us almost 0 or close to 0. So that tells us that there's no linear relationship between the two variables here, y and x, when R is close to 0. Normally the R value, which is again the correlation coefficient, will be a value from -1 to +1. If it's a negative value, that means we have a decreasing relationship. When s increase, y decrease. Or we can say that when y increase also, x decrease. But again, here we use the s as our independent variable. So the s will determine the y. So that will lead us to the concept of regression analysis. So from the previous lectures or the previous section, we said that the correlation coefficient was used to measure the degree of linear relationship between two variables. However, it does not describe the exact linear association between x and y. It just tells us the degree, the strength of the relationship between the x and y or two variables. So that is the role of a regression analysis. Regression analysis would describe the exact linear association between the x and y. And also we can use the regression analysis to predict a future y value if we know the value of x. So by determining a specific relationship between x and y, we may be able again to use x to help predict y. So we always say that in order to do a regression analysis, first we have to check if there's a linear relationship between the two variables. So earlier in the section also, we defined the equation of a line to be y equal to ms plus b, where we said that the m is the slope, the b is y-intercept. However, in traditional statistics, again, this concept, as we said earlier, is college algebra. But in traditional statistics, uses a different symbols for the slope and also for the intercept in the equation of the line. Now, instead of B, we are going to use BO to be the symbol. Basically, this will tell us that when S is 0, the value of Y, describe the Y-intercept. And also B1 will be the symbol used to represent the slope. So in this case, we are going to say Y equal to B1X plus BO. So Y equal to, again, BO plus B1X, or B1X plus BO. So now BO is our Y-intercept, B1 will be our slope. Now, by providing BO and B1, now the relationship between S and Y is completely specified. So the linear equation relating X to Y is also referred to as a mathematical model. So we should know that the value of Y is completely depending on the value of X. So we will say that X is our independent variable and Y will be our dependent variable because S will determine the Y value. So how do we measure how close a line is to the data? So this concept will bring us to finding the error. So here we are going to have two values of Y, the predicted value after we find the best line fit and also the actual value. The goal of getting the best fit line or the line that is close to the data means the error, or we use the term residual. That's the difference between the actual value and the predicted value on the line is minimal, then that will be the best fit line. So here we say one possible method of choosing the best fitting line is to use the line to predict the Y value for each observation. Now, the superior line is the one that does the best job of predicting the observed Y values. So let's look at some small data example here. So here we have X and Y, two variables, and we have their data set. So what we're going to do is to plot our data set. So when we plot this data set, we are going to get this equation, but let's see the data set. So this is the graph. When we plot it, again, one thing is also a lot of statistics applications such as Excel, SPSS, we can determine the best fit line. And also by determining the best fit line, the application will give us the equation, but also we can solve it manually. And that's what we are trying to do here. So the first thing we do here now is that we have the actual value, the observational value. Then we plot our line, then we get the best fit line. Now we can see that there's a vertical line between the actual point and the Y. That will be the difference of the actual value will be the point. So in this case, Y is 3, my first point here. And then the point vertically on the line will be the predicted Y value. So the difference between the two will give us the error. So that's what here we are saying the observed values are the actual point and the predicted values will be on the line. So each point we have a vertical line to the best fit line. So that is the concept here. Now, as we said, you can use Excel or SPS, any statistics application to create the concept here. The system will find the best fit line for us and it will give us the equation. Here we are going to do it mathematically. So there's a formula that we can use to find the Y-intercept and to find the slope. As far as we know the values of X and Y, we can be able to find the slope and we can be able to find the Y-intercept. Then from there, we get our equation. So here we say, although other lines might do a better job of fitting the data, let's see how well this line predicts the Y values. Now, in order to evaluate how well a given line fits the data, first we must construct a method of measuring how well any line fits the data. So here we say if a reasonable measurement is developed, then it can serve as a decision-making criteria, which will enable us to look for the best fit line or the best line. Now, to develop appropriate criteria, we need to examine the purpose of the regression line. So this is y equal to BO plus B1x. Again, BO is our y-intercept, and B1 is our slope. So this is the points that we have, the S and Y. This is given to us. And as we said, if these two values are given, the two variable values are given, we can create the model. Now, when we use, let's say here we are using a software. So when we use the software, we came up with the predicted line equation, or we'll say the regression equation or the model. And based on this model, now we can determine the Y predicted value. So when S is 2, the predicted Y will be 2.4. When S is 4, the predicted Y value will be 3.8, 4.5, 6.6. Basically, what we are doing, we are substituting the S values into the predicted Y equation, which we call the regression equation. So that's the difference here. Well, then we can see the error. Now, why do we have an error square? Because normally when we have error, some of the error will be positive, some of the errors will be negative. So when you add them together, sometimes we may even cancel. Here, imagine our error is negative 0.6. That's not good. It should be at least a positive value. So this tells us that the best way to find the error is to find what we call the sum square error, SSE. When you find the error, we square each error so that we take the negative out. Then we sum all together. So this is our total error, sum square error, 8.90. So our goal for a best fit line is to have the minimum SSE value. Or if possible, if SSE value is 0, then that's perfect, which means the predicted is the same as the observation. So it's perfect, 100% correct. So how do we measure how to cross a line? Is to the data. Again, how do we measure how close a line is to the data? As we said, everything is based on the error. So the difference between the observed value of Y and the predicted value of Y is called the modest error. And as we saw in the previous example, we have to square the error, then we sum them. So everything depends on the value of SSE. The lower the value, that means the close the line is to the actual data. So here we see one possible criteria that could be used to compare different lines that might fit the data will be to sum all the errors. We have to sum all the errors and choose the line with the smallest sum. But as you can see in the previous table, as we saw it in our previous table, we can go back one, we saw that the sum of the errors give us negative value. That's not good. So by traditionally what we do is that we are going to square each error. And that's what we are about. As you can see in the previous table, some of the large positive errors were cancelled out by equally large negative errors. It is possible to develop a line that has a small sum of error, but the errors themselves are quite large. So that's why, again, we have to square the error. So that's the sum of the errors is not the criteria we have been looking for, but it is close. By squaring the error terms and then adding the square errors, there are no negative errors to cancel out positive errors. So that's more better. It is the same concept as finding the variance or standard deviation. So this is the formula we can use to find the sum of square errors. Again, Y caret means the predicted Y value, which will be on the line, and the Y will be the actual value. So the difference of the actual Y value and predicted value, we square it. Then we sum all, if we have 10 data, then we sum all the 10. And that will give us the sum square error. So the goal is to minimize the SSE, and that will be the best fit. Also, we have what we call the least squares lines. So the SSE, again, can be used as a criterion for selecting the best fitting line through a set of points. Now, if SSE is 0, then the model fits the data exactly, and the observation data must lie in a straight line, which is perfect. Now, if line A's SS is larger than line BSS, then we will say that line B fit the data better than line A. Why? Because line B SSE is smaller. Line A SSE value is larger. So as we said earlier, the best fit line is a line with the less value for SSE. So for the model that we did, we found out that the value of SSE is 8.9 from the example. Now, without studying other possible lines, there's no way to judge whether the line is a large or small value of SSE. We can try another second or third 3 lines and see which SSE is lesser, then we take that line as the best fit line. So that's what we mentioned here. If there were a method that would find the best line, the line with the least sum of square errors, then our problem will be solved. This best line will be called the least square line since it has the smallest SSE. Now, these are the formula we can use to, again, as we said earlier, you can use Excel or any stat application to come up with the regression line or the best fit line and also the equation. But we can also do it manually. Now, if I have X and Y values, I know the size of the sample. So to find the slope, it will be the size of the sample times the sum of X and Y values, observations, minus the sum of only X values times the sum of only Y value. Now, there's difference between these two. Here, we are going to multiply X and Y first for all the values before we sum it. But here, we are going to sum X, then we sum Y, then we multiply the two together. Then we divide by the size of the sample again, the sum of X squares. So this means we have to square all the values of X, then we sum it. But here we have sum X all square, which means we have to sum all the value of X before we square. So that will give us the formula to find the B1. Then to find the B, again, B1 is the slope. Now to find the B0, which is our y-intercept, is the difference of the yi values, depends how many values we have, and the sum of all of them minus B1 times the sum of si values. So this means add all the y values, then add all the s values, then we multiply the sum of the y values minus the slope times the sum of s value. Then we divide by the sample size, and that will give us again the y-intercept. Now, if we know the slope, and the B1, which is the slope, B0, which is the y-intercept, then we can come up with the regression equation. Because the regression equation will be the y caret equal to, again, BO plus X, and then B1. So any value of X, I can determine the y caret or the predicted y value. So the interpretation of BO and B1, we said that the intercept coefficient, which is the BO, is the average value of the dependent variable, the dependent variable Y, when the independent variable X is equal to 0, as we said. That's why we call it Y-intercept, the Y value when S equal to 0. Now the slope coefficient, which is B1, is the average change in the dependent variable Y for one unit change in the independent variable X. Same concept as a slope in college algebra. So the B1 will determine the steepness of the straight line. So that will be the conclusion of these lectures. Again, in these lectures, we cover the concept of a best fit line and how we can come up with a regression equation and also the best fit line using bivariant data set, that's data set with 2 variables. So again, wish everybody the best and thank you for your time.